I just have to be careful not to stop the recording, so I'm just gonna close that. Alright, so two exercise I'm gonna cover, which is the derivative of natural exponential e of x, and also natural logarithmic function, so log of x to the base e. The rules are not very difficult. The trick is, as the functions get more complicated, you're not going to have a simple differentiation. So the main target, what you need to get out of those two exercise, is the use of the chain rule. And I'm going to heavily use the chain rule using the two methods, so either f of g or using a temporary substitution using a notation u, which is the Leibniz notation. Yes, Elia, I can see your message, so I'm going to do that now. Now I have to rearrange my side of it. I need the chat on my first screen. Well, you can't have it all. It will be on the recording. All right. So okay, with the derivative, so e of x, e is what we call the Euler's number. It's a constant. It's about 2.71. Now the special property is, when you have that function which is e of x, its derivative is exactly the same. Okay, so the derivative of e of x is the same as its original function. Now if we move on to a composite function, so a function of a function, here you have your first function is kx and your second function is e of x. The derivative is factor k times e of kx. Now using a chain rule, I will prove you that you get the answer. So you need to know the first one. The first one is the easy one, and let's go through that proofing using the chain rule. Fine, I'll do the example first. Alright, so the example again is using a you're gonna use a chain rule, so it's a 3 times e of 2x minus 1. Using the Leibniz notation, u is 2x minus 1. Okay, then we can differentiate those two. So y now is a function of u. You do dy over du, and here it will be du over dx. So you find the respective derivatives. Okay, and then you use, remember the question, what you're trying to find out is dy over dx. So dy over dx is going to be the product of dy over du times du over dx. So we do the product of the two. Now again, the derivative needs to be in terms of x, and we need to substitute that u function back over here, which is 2x minus 1. Okay, so it's going to be 6 e of 2x minus 1. So another example, here you have an exponential. very typical to have the exponential. They mix it up with a fraction, and it shouldn't be too much of a problem. All you need to do is think about your index law using negative power. So when you have a fraction and your base is on the denominator, you can turn it back into the numerator by changing the sign of the power. Okay, so now it's just e of negative x cubed bracket 2x, and again we use a chain rule. Okay, so let's see which notation it's going to be. So we expand the bracket, that's fine. So again we use the Leibniz notation. So the all first function that is started before your exponential, it's u. That's a function in terms of x, and the second function y, it's going to be in terms of u, it's e of u. We differentiate u in terms of x, y in terms of u, we get those two, and to find dy dx, it's going to be the product of the two. Again, it's going to be e of u as a factor, so e of u is here, that's your dy over du. What you need to do is substitute u by what you define here, it's negative x cubed minus 2x, and you get that that function. I think that we just leave it as it is. Yeah, that probably you can factorize that negative if you needed to. It's again the idea is when you differentiate, you want to find out when it is equal 0 to find your turning point. And later on, when we look at looking at the graph of a function using the derivative, we're interested in the sign as well. So the more you factorize, so you have a negative one here, the more you factorize the factor, the easier it is to determine the sign of the function. So depending on your x values, your derivative will have a specific sign. So if it's equals 0, that it's 0, but either side of 0, it will be negative or positive, and that's what you're interested in. So if your derivative is positive, it means your function is your original y function is increasing, and if it's the derivative is negative, your function is decreasing. So here, yep, they factorize it again. Okay, so we leave it like that. We don't need to do the interpretation for this part. So that was the derivative of an exponential. Okay, so now let's look at the logarithmic function. If you have a log of kx to the base e, its derivative is 1 over x. Okay, now that's where the proofing is. So let me have a think. Again, just be mindful about the domain. So it's r plus. You want all of that to be positive. So if x is r plus, it implies the coefficient is positive. Now if you have a coefficient that is negative, it's not a problem. If your coefficient is negative, you need to change the domain for x. In that situation, it will be r negative. Okay, so it's 1 over x. Now this is a little bit of a proofing using what you need to do. Let me go back to, no, I just continue, that's fine. So what is it doing? Okay, so it wants to show. Now in order to show you that, what you're going to do is we're going to go back to the exponential. So remember the exponential, if it's exponential in terms of x, if you differentiate in terms of x, it's the same. So what we're doing is we look at that log of e function, and what we're going to do is we're going to transpose to make x the subject. We're going to end up in a function as a function in terms of y. We're going to differentiate in terms of y, and we're going to go back to determining dy over dx. So here that function is y over equals log of kx over e. We do a little bit of transposition, there's a little bit of working out. X is equal to e of y over k. So that function x, we can now differentiate in terms of y. So that gives you the same, and the coefficient k remains. So now what we have is that equality, and we can now substitute ey. We know it's also kx, so we substitute that ey as kx, which is over here. That simplifies to x. So now we know that dx over dy is equal to x. We do the reciprocal. That's a rule, so you need to remember that rule. It's not really an inverse of the fraction. It's just that that relationship between those two is linked to the first principles, the rate of change, and basically dy over dx is 1 over dx over dy. Dx over dy is x, so it's going to be 1 over x. Okay. Example using application. Again, you will not necessarily find a log on its own. So here you have a composite function. So the first function is 1 minus 3x, and the second function is log to the base e. So here again, what you need to do is using a chain rule. So you can substitute the 1 minus 3x by g. Here we're going to use the Leibniz notation, so it's a u, and y is going to be log of e, and all of that is a u now. So we can differentiate respectively u in terms of x, that's negative 3, y in terms of u, that's 1 over u, that's from the previous slide. We do the product of the two, that gives you negative 3 over u. You substitute 1 of minus 3x. Now just be mindful here, you have a negative and you have 1 minus 3x. We always like, if possible, to rearrange it and to make it neater. We want to have a positive. So that negative we're going to combine with the denominator. And when you do the negative in an expression, we just swap around the sign of each term. So here that will be negative 1 plus 3x. And adding terms is commutative, so you can swap the order, okay? And it's going to be 3x minus 1. Now for some of you, it's going to be on the recording. I'm actually waving at the camera, but you can't see it, so you're missing out. But if you want to go back, you can see it on the video. Alright, so let's say you want to differentiate another example. You want to differentiate another function. Again, it's a composite function. You need to apply the chain rule. So here again, we have a u, which is this one. The y is going to be 2 log of u to the base e, which is down here. We differentiate each one of them. We do the product here, that's dy over dx. And we're going to substitute u by the expression, which is 3x squared minus 1. Okay, so we factorize that. Simple single fraction, 12x is 3x squared minus 1. Now the denominator, you don't need to factorize it yet unless you want to find the sign of it. Okay, so let me fix that. I'm gonna lock that. Alright, sorry about that. Now I locked the session, so if you have anyone that from this class that want to come in later, can you just let me know so I can unlock the session? Oh, this is the first time I have to do this. I did it pretty well. Okay, let's move on to this. Now, the way I want to focus on this, yes, here it's kind of factorized. The denominator is not factorized, so it's a difference of two squares. You need to know again with the quadratic how to factorize it. Again, later on you'll find out when you move on, the application of the derivative is you want to find how your function is behaving, if it's increasing or decreasing, and to determine its sign you need to factorize as much as you can. So ideally when you have a polynomial, what you want to have is have different linear factors. Alright, let me unlock that. Alright, it's unlocked. Now I need to lock it again. Alright, so with this, yeah. Alright, so now what we're gonna look is there's also a generalization of the rule. Again, if you use the chain rule, you don't really need to know all that, but the idea here is if you have a log function that is combined, it's a composite function. The first function is a linear expression, so it's ax plus b. The second function is log of e. Now do remember the domain. So the domain for log of e, we need to have ax plus b to be greater than 0. And if we rearrange that in equation and make x the subject, that's what you end up with. Okay? Now the derivative is going to be, you have a coefficient a that will be on the numerator, and the denominator is going to be ax plus b. So the generalization here is if you have a log to the base e of a function, what you need, the derivative of that is going to be a fraction, the denominator is the function, and the numerator is going to be the derivative. Okay? So if I do, for example, if I do log of e of, let's say, x squared, okay, what you need, if you want to differentiate, or the denominator you write x squared, the derivative of x squared will be 2x, so that will be 2x over x squared, and I will simplify. Okay, but that's the idea to do when you want to differentiate a function that is a composite of a log of e of a function. Yes, we're starting with this. For a log to the base e, the domain for log to the base e, or any base, is the expression needs to be greater than 0. So that's what you start with. By making x the subject, you end up with that inequality. I would advise you to start with this. Okay, the reason why is if a is negative, that's kind of changing the inequation a bit. This works only if a is positive. If a is negative, what's going to happen? You're going to have to change that to a less than. Okay, so don't necessarily memorize that. What's important is you go back to the original expression and you look at it and make it positive, and then you manipulate that expression to make x the subject. And that's it for the two exercises of today.